Hey there, welcome to the lab. As you can see, I'm in my lab coat and safety goggles because safety is a priority here at the University of Pittsburgh. For today's experiment, we're going to be talking about bomb calorimetry. Now, bomb calorimetry is very interesting because you can use it to find enthalpy of combustion. And why is that important? Why do we care about that? Well, combustion products are things that we see every day. You use them in your car for gas. Food is a combustion product, and the sun uses combustion to provide heat to the entire planet. Now, your basic bomb calorimeter is going to have a couple parts. It's going to have a water bath that holds the bomb, which is going to be a sealed container. The ones we'll be using in this lab are oxygen bomb calorimeters, which keep the constant pressure of oxygen in the bomb. You have the ignition wire, which provides heat for the reaction, and you have a stir, which will keep the water in motion and allow the temperature meter to read correctly. It's important to keep the bomb at a constant pressure and a constant volume because having only one changing variable allows you to attribute that to the reaction process, which we're measuring temperature here. Now, once you have the enthalpy measured, you can use the enthalpy to find enthalpy of the entire reaction process, which is very useful because some compounds are toxic and hard to work with, so you can attribute one of the reactants and one of the products to the other reactant. So the basic chemical process that we will be observing in this experiment is the reaction between benzene and cyclohexane under heat in order to form cyclododecatriene, or CDDT for short. Now, this process will allow us to find the resonance energy of benzene because cyclododecatriene and cyclohexane and benzene each have the same bonds and same number of bonds between the carbons of the molecule. So the only thing changing is that we're breaking the aromatic system of benzene and taking away that extra stabilization energy from it. The first hypothesis that we propose here is that using Hess's law will allow us to determine the resonance energy, and it should correspond to the enthalpy difference between cyclohexane and CDDT. So for our second hypothesis, we are going to propose that the heat of combustion of CDDT will be higher than cyclohexane. Now, this makes sense because cyclohexane has no conjugation, they have no double carbon-carbon bonds, and it has less bonds overall. So CDDT should combust and provide more heat than cyclohexane would because it has more bonds to break, it has more energy to offer, and it's just a more energetic molecule overall. So the basics of our experiment that we're going to set up is we're going to measure the heat of combustion for cyclohexane, the heat of combustion for CDDT, and compare that to find the enthalpy of combustion of benzene as well as its resonance energy. Now we relate the heat of combustion to enthalpy by determining the number of moles that change and the number of moles that combust, and multiplying them by the gas constant and the initial temperature, and then adding that to the heat of combustion to find the enthalpy of combustion. And then the heat of combustion we can find by measuring the temperature change during the combustion process and multiplying that by the heat capacity of the actual bomb portion of the bomb calorimeter, and that will allow us find the heat of combustion. As stated before, we need the number of moles of each compound in order to relate enthalpy of combustion to heat of combustion. So the basic setup is that we are going to weigh cyclohexane or CDDT into a small gelatin capsule and then place that into the bomb portion of the bomb calorimeter. And then this bomb gets pressurized under an oxygen environment, and that gets placed into a water bath where the ignition wire is connected to the inner portion of the bomb touching the gelatin capsule. Now the gelatin capsule will be consumed during this process, but it's important to take the mass of that out in order to only have the number of moles of the compound. Now, the temperature change will provide us with the heat of combustion for each of the species of interest here, and then that will allow us to calculate the resonance energy of benzene. So the readout that you get from this combustion process is something like this curve here, which drastically increases and then plateaus as the temperature gets higher. Now, the points of interest for both trials here are the initial temperature, which is corresponding to Ti. This value is the temperature where the water bath has equilibrated about a minute into the process. Ta corresponds to the ignition time and the ignition temperature. Tc is the max temperature of combustion. Tf is the final temperature of the process taken, and then Tb is 60% between Tc and Ta. And this point is important because from Ta to Tb, the correlation is fairly linear, which more easily allows us to find the heat of combustion by using a linear relationship. The same data is obtained for CDDT, as well as the same points are found and the same points are marked on each of these curves. Now that we have our data, there's really no need for a lab coat and goggles, because no more dangerous chemicals to deal with. Anyways, so after the runs, we can find the heat of combustion for cyclohexane 1 and 2, for CDDT 1 and 2, and then the specific heats here listed are the specific heats of the bomb that was used, as mentioned previously. The delta T is found, as well as the number of moles. Now, all of this allows us to use the previous equation to find the enthalpy of the reaction, which is what we're after in the first place. Importantly enough, though, the reaction process is in the gas phase, so we need the enthalpy of vaporization for the compounds that we've worked with. So the enthalpy of vaporization for CDDT can be found by using this linear relationship here. The enthalpy is related to the inverse temperature as well as the natural log of the pressure under which this process takes place. And the linear relationship here, basically the slope is your enthalpy if you take the slope, multiply it by -1, and then also multiply it by the gas constant. So what does this mean? Why do we care? What are we trying to find in the first place? So hypothesis 2 was proven correct. The enthalpy of the CDDT was in fact higher than the enthalpy of cyclohexane. Now, the resonance energy can now also be determined by using Hess's law. Now, we actually have a really good tool that allows us to model the heat of formation for cyclohexane, benzene, and CDDT. We use Cygress as a modeling software for this, and this is what gives us our theoretical value of the resonance energy for benzene. You take CDDT, the heat of formation, minus the heat of formation of benzene, and then minus the heat of formation of cyclohexane. Now, this theoretical value allows us to calculate our error in our values based on our experimental to our theoretical. Interestingly enough, though, the enthalpy between CDDT and cyclohexane did not fully correspond to the resonance energy as was expected by hypothesis 1. This leads me to believe that it's not so simple as just taking the difference between the two, because Hess's law had to have everything in the gas phase as opposed to the liquid phase, which is which the enthalpy of combustion was calculated from to carry out this reaction. But the overarching theme is that resonance leads to more stabilization for the molecule, and it allows benzene to have a more stable molecule than it initially would if there was no resonance. So this experiment was pretty standard, but some things that could improve the overall design is we can compare other methods of benzene formation. For example, we can use a long chain triene molecule to form benzene, And we could also use a larger sample mass because that might allow less deviation in the data collected. And then trials should probably be reproduced more than just 2 times in order to have more accurate data. And then the enthalpy of benzene could be measured directly in a controlled inert environment under nitrogen or under some sort of inert gas or in a glove box or something like that. These are the references that were used for this PowerPoint, and hopefully I'll see you in the lab next semester.